We have three speakers today. We started the webinar a few minutes early and it was sitting there idling on the screen. So we have three speakers today. In a moment, I'll introduce Duncan Josh from Atkins. Duncan, I will switch to your screen in just a moment. So if you're standing by and ready for me to switch that over, we'll leave it on this screen for now. Duncan will be speaking about future-proofing infrastructure. Next will be myself discussing the future of the gas grid and some low-carbon heat demonstration projects. And then we have Dr. Letitia Motet, who will be discussing her project on low-carbon, climate-responsive heating and cooling of cities. We will aim to wrap up each talk with some time for questions. So please type your questions in the boxes at any time throughout the webinar, and we will try to get to as many of them as we can at the timing of the webinar, but we can do email follow-ups as well. Everyone who attends the session will receive a CPD certificate, so this will be sent along to you tomorrow, along with the link of where you can find this recording. Okay, so let me try to switch over the screen to Duncan now, and I will introduce our first speaker. So Duncan has been interested in low carbon sustainable energy systems for many years. He has contributed to research for and co-authored the Zero Carbon Britain report presented to government ministers in 2007. Duncan has been with Atkins since 2008 and has worked on a wide range of decentralized and low carbon energy projects. He's provided advisory support for government, including the Energy Storage Innovation Program, and from 2017 he's been a part of the team working on decarbonizing the energy systems of a major UK airport. So Duncan, over to you.
Thank you, Aaron, and good morning, everyone. Aaron, can I first check that the screen is coming through okay?
I'm not seeing your screen on the display. I think you have to probably accept the change of presenters. We'll give it a moment to work. Okay, there we go. Now we can see you. Thank you, Duncan. All yours.
Okay, that's brilliant. Thank you, Aaron. So good morning, everyone. I'm Duncan Josh and I work for Atkins, and I've been working in the field of low carbon energy for quite a few years now. And today I will be presenting on decarbonising our thermal energy systems and future-proofing our major infrastructure. So the presentation will briefly look at how we currently use energy in the UK, how we are progressing on the road to zero carbon, where will our future low carbon energy actually come from, and this has potential significant implications on how we design our local energy systems, and then to look at some international examples of large-scale low-carbon thermal energy systems, and then to conclude with a UK example from a major project that we've been working on for several years. So firstly, how do we use energy in the UK? So this shows primary energy consumption by sector as prepared and extracted from Dukes. So we can see that the domestic energy sector is a major consumer of energy, only surpassed by transportation. And transportation obviously has a long way to be fully decarbonised. So the domestic energy sector represents around about 450 terawatt hours of energy, which is larger than the total UK electricity consumption in the UK by around a third. So in terms of gas consumption by sector, again, we can see that the domestic area or domestic sector is a significant user. In terms of the demand consumption profiles, we actually saw an increase in gas within the public administration, commercial and domestic sectors in 2018. This was largely attributed to a rise down to very cold snap of weather in February and March, known as the Beast from the East. So worth bearing in mind that even if we do see progressive warming of our climate, we still have to be able to deal with very cold snaps as well. So how are we getting on our road to zero carbon within the UK? This chart shows the historic and projected carbon emissions, again by sector, as prepared by BEIS, and this is under the central emission scenario. It includes policies and the implication of those policies. We can see from the grey line here, which represents the energy supply for the UK, that there's been good and progressive rapid decarbonisation of the overall energy supply. That is forecast to fairly plateau from 2020 through to 2035 with some small decreases. The total greenhouse gas emissions seem to actually not make much progress from 2020 through to 2035. So next, if we zoom in on three of the most stubborn sectors, here we have the business, residential and transport sectors. We can see that the residential emissions are actually forecast to grow between 2020 and 2035. So that's a brief look at the projection of our emissions. So how are we going to supply our low carbon future energy systems? So obviously we have wind and PV, which have made good progress over the last decade, both variable in nature. Wind potentially supplies 24/7, but has still a variable output. It's generally higher output in winter than in summer. PV obviously has a daily pattern, but also a large seasonal fluctuation. Nuclear can provide good base load, but limited capacity within the UK. Biomass, which provides a firm supply, but there's potential issues with the sustainability of the supply lines. Hydrogen, possibly reformed from hydrocarbons such as natural gas or generated via electrolysis, for instance, from renewable energy or potentially nuclear, but mainly considered as an energy rather than an energy source. Tidal, which is regular and predictable, and the UK has fairly good resource. And then wave, which again, UK has very good resource, but it's a very harsh environment within the sea, and also has to compete with offshore and has a similar kind of variability to offshore wind as well. And then potentially natural gas with CCS. So if we are going to rely much more on wind and PV, for example, then how are we going to manage those supplies into our systems? So this shows the wind output daily averages from last year. You see a significant fluctuation that is very rapid from day to day potentially and over periods, and also generally kind of lower output in summer rather than winter. So we can see the average is significantly lower than the peak demand, the peak supply, sorry. So this is the generation mix as of a day in November last year. So this is a typical kind of winter day. And this shows the output over the course of a calm day. So this light creamy yellow band represents wind power. You've got your interconnectors along the top, some biomass, which is good and stable. Then you've got your natural gas making up the variability. Base load provided mainly by nuclear, and then a little bit of coal. If we look at the subsequent day, which was a windy day, we can see a massive expansion of wind power output across the course of the day. And it's mainly the natural gas that provides the flex in the system to accommodate the fluctuation in that wind power. So going forwards, if we are to remove gas, then how are we going to accommodate these major fluctuations? This is the output for PV across last year. So this is day averages. So even though the peak is around 9.6 gigawatt, the average of it is around 1.3 gigawatts across the course of the year. Very, very low output during the course of the winter compared with the summer. And then we can still see on a daily basis, there's quite significant fluctuation still as well. Sometimes you have major difference in the output from the PV from one day to the next day. So this is a Sankey diagram prepared within Dukes, and this shows the renewable energy contribution from the current UK mix. We see the solar PV, wind, and some wave and tidal. making up around 2/3 of the renewable electricity. You can see the other third coming from fueled biofuel sources mainly, and some waste as well. But also have noticed that from the fuel sources, there's almost 70% of the energy is lost through the conversion process. So again, this represents a very good opportunity to actually utilize more of that energy and not just waste it through the conversion. See that there's a contribution from heat pumps that's similar in order of magnitude to that of PV, even though it's not quite drawn to scale for some reason on the Sankey. Just to put some of the numbers into context, this represents our domestic energy consumption across the course of the year, of which a large proportion is made from domestic gas. If we look at the contribution from wind and PV, there's a significant amount of additional generation required to get anywhere near fully decarbonising these sectors. Transportation as well, through the use of EV or potentially hydrogen, will need a significant amount of new low carbon energy into the system. So what are some of the options to help with decarbonisation? So from context of the built environment, obviously improving efficiency and maximising resources is key. So fabric first approach, obviously, with reducing demand as much as possible. Following that, it's very important to develop a good understanding of the remaining demands, both the current demands and the future demands. So where the use of a building may change, or where climate change may also have an impact on potentially increasing cooling loads and decreasing heating loads, etc. Then efficiency of the delivery of the thermal energy, very important, and potentially buildings can become proactive energy management contributors, so providing demand side response and energy storage within the building itself to help with the increased variability from our low carbon supplies in the future. They can also act as generators and collectors, so solar and waste energy can potentially be collected and then reused. And then this waste energy can potentially be shared either within the building for different uses or externally via energy networks. And then the application of energy storage, be it electrical or thermal at a building level, but also beyond the building, where it makes more sense to actually use energy storage for a collection of buildings or a site or potentially a district energy system. So this is an example of the solar resource and roughly what lands on the Greater London area each year. So if we look at the overall area of it and look at the typical resource of 1,000 kilowatt hours per meter squared, gives us around 1,600 terawatt hours. If we could harvest just 1% of that, that would represent 16 terawatt hours. Now the harvesting of this may be through direct solar energy, but it may also be through recovering energy from buildings that could be overheating, or via rivers, lakes, ground, etc., which are all absorbing solar energy that can then be reused. And against the London gas sales is around about, that would represent around about a quarter of the total London gas sales across the course of the year. So now we'll look at some large-scale thermal decarbonisation systems. So this is an international example from Helsinki in Finland. So this was completed in 2006, and it's a combined district heating and cooling energy network, Katrivala. And the facility provides simultaneous heating and cooling. So there's around 90 megawatts of heating, 60 megawatts of cooling via a set of large heat pumps. So it uses the sea both for heating and cooling. It also uses the energy collected in the buildings, which is effectively transferred through the district cooling system, and then back to the centralized heat pumps, which can then be reused to provide heating to other users on the system. It also incorporates sewage heat recovery as well. This is Marstal in Denmark. So this is a district heat network serving a local town. So the town includes residential, hotels, schools and leisure centre. And the system is fueled by a number of different sources, including biomass and solar thermal. So they use an extensive solar thermal arrays and the application of a large-scale energy storage or interseasonal energy storage system. So this is a PTS, or a pit-based thermal energy storage system. This is it during construction. So this allows a lot of energy that's collected during the summer months to be stored and then used for the district heat system across the winter. They also use heat pumps to improve the effectiveness of the store to be able to drain down the heat effectively and provide a larger temperature difference to make the solar thermal more productive as well. So now a quick look at some areas of thermal storage and what some of the implications may be. So this chart represents most of the larger scale thermal storage systems within Europe. So it shows the investment cost per equivalent cubic meter of water. So that's a euros per cubic meter, ranging from around 450 to 500 down to around the 30 mark for the larger systems. So this is Marstal, the system that we just looked at. So Marstal comes in around 30 euros per cubic meter. So if you're operating with a 50-degree temperature difference across your thermal storage system, that comes down to around €1 per kilowatt hour once you've accounted for losses and inefficiencies in the system. This table shows the typical installation cost per kilowatt hour for electrical energy storage. This is generally at a much smaller scale. So this is prepared by ARENA, and it shows the 2016 and the 2030 projected costs. So for lithium ion technologies, and there's a number of chemistries here that are shown, you're looking at around $400 to $1,000 per kilowatt hour in 2016, with a drop going down to about 150 to 400 by 2030. It also shows flow batteries in here and the price that they're expected to drop down to by 2030. Now, obviously, this is applicable to short duration storage, so I expect to be cycled a lot more frequently. But when you look at it against the typical cost for large-scale thermal energy storage, there's a massive difference in orders of magnitude. So certain storage technologies will be very useful for short duration fluctuations, but very poor in being able to provide smoothing over a longer duration. So now we'll have a quick look at a UK case study. So this is a major project that we've worked on for a number of years, which is looking at decarbonising the ground operations of a major UK airport. So one of the first steps in this process was to look at the demand profiles for the airport. So this graph shows the thermal demands, and the top line here is the peak monthly. So that's the peak that's experienced in any month for most of the assets at the airport. The purple line shows the average on the peak day. So if you fully smoothed the peak out on the peak day, you would result with this line. The average load is shown by the orange block. So this is the monthly average for heating, and then the monthly average for cooling is shown on the negative axis, so we can look at the contrast. This line represents the net balance. So again, this is the same graph simplified, showing the net balance between the averages across the month for both heating and cooling. So what happens if we potentially could time shift the cooling load by the course of 3 months? What shape does it give, and what's the net resulting load across the year? And again, if we could shift it by 6 months, this now represents the net resulting load. So if you had perfect storage and capturing and reuse of the opposing thermal energy systems, you would end up with a similar profile to this. This doesn't account for additional heat from heat pumps, etc., from the operation of them, so it's not quite true, but it represents the indicative profile that you'd end up with. And this would then represent the imported energy that you'd have to bring into the site, because this amount would be balanced across the course of the year. So very important to identify what the local thermal resources are for any project that you're trying to decarbonise from a thermal perspective. So number one was the harvesting of simultaneous heating and cooling loads for this site, because there was such a good potential overlap. So there's overlap on a daily basis at different times in the year, but also when you're looking at introducing, relatively short duration storage, but then also long duration storage. There was also investigations for the aquifer below the site, the lakes, reservoirs and ponds around the site, rivers, the sewer system, and also ground and air. So all of these systems would be coupled with heat pumps to be able to interface. And the simultaneous heating and cooling loads would also be dominated by the application of heat pumps to be able to provide balancing with those integrated with thermal storage. So it's very important to look at options for thermal storage for any site. This project was fortunate in that it had the ability potentially to incorporate interseasonal storage. So both PTS, that's pit-based thermal energy storage systems, and BTS, borehole thermal energy storage systems, were fully investigated. PTS was more favourable for a number of technical reasons, and also to do with the availability of land. And then tank-based thermal energy storage systems were reviewed for the application for daily storage. It's also proposed to adopt the use of a common thermal network, or CTN, which is effectively an enhanced ambient energy loop for thermal energy transfer between the different loads, the supplies and the storage mediums. So on to the summary conclusions. So number one, a zero carbon energy system cannot be achieved without an integrated holistic approach. It's very important to look at the wider system as well as particular technologies. The current UK carbon energy projections do not support a UK trajectory to zero carbon. There's obviously a lot of work that's still needed. And there is no single silver bullet on the road to zero carbon. There'll always be a collection, a portfolio of different approaches and different technologies. And all energy engaging assets will ultimately they'll need to maximise their efficiency and, where possible, capture and reuse waste thermal energy, because as we move forwards to decarbonise, there's going to be a real shortage of actual energy supply coming to the system if we want it to be all low carbon. Anywhere where there are heating and cooling synergies, these should be utilised as close to source as possible, and where not possible, then these could be exported via energy networks and then used as locally as possible. And energy storage will become ever more critical, delivering a stable zero carbon energy system as we see more and more variable supplies coming into the system, plus changes of demands. And large scale thermal energy storage can achieve very low cost energy balancing. This is far in advance of many other storage mediums. However, to get the maximum benefits, you can only achieve this when combining it with large thermal energy networks. Thank you.
All right, thank you very much. Thank you, Duncan. That was really interesting. So I saw quite a few questions sort of come through there while we were speaking. So we will come back to those at the end. I'm going to change the presenter now to my screen and do the next portion of the presentation. Okay, so hopefully everyone can see this slide here now with the UK after gas. My name is Aaron Gillick. I'm an associate professor of energy and building systems engineering at London South Bank University. What I'm particularly curious about with my research is this transition to low carbon heating and sort of the system implications of it. So in particular, how do we see interactions happening across sectors and disciplines? So how the large national scale policy changes actually get transitioned and impacted and implemented down at the sort of local supply chain level. So I think one of the most important ingredients in that is really good, effective demonstrators to sort of show what can be done. And so that's what I wanted to talk about today. Overall, when we talk about decarbonizing heat in the UK, what that really means is ending the use of gas as we know it, of natural gas as we know it. And Duncan did a really good job of sort of describing some of the headline issues around how our energy system breaks down and just how big a challenge this really is. So, and the UK government has more or less said specifically that this is the toughest sector of all. Like obviously there are challenges with transport, industry, the power sector, and all of that. They are challenges, but there's at least a foreseeable path towards decarbonizing those sectors. Whereas with heat, it really does require effectively getting rid of every single gas boiler that's installed at the moment, switching them to something else, hydrogen, electricity, but it effectively means getting into every single home and business in the country that doesn't already have a low carbon system, which is almost all of them. So it's a big change. It's going to involve almost all of us. And the reasons that it is such a big challenge, I think, are very well demonstrated by this graph, which sort of follows on from what Duncan was showing. What you see is, it's a great bit of research by Grant Wilson at the University of Birmingham. So what you see on the bottom here is the electrical supply over sort of a typical / cold week in the winter. And it sort of caps out at around 50 gigawatts, which is again consistent with Duncan's slides there, right? 50 gig. When you see a scale like this, gigawatts, think power stations. So 1 gigawatt is 1 power station. That's everything that the electricity grid can do. And it's just dwarfed by the amount of gas consumption that we have. In two very important ways. First of all, the area under the curve, just the total sum of gas that we use in kilowatt hours throughout the year is enormous. You know, it 5-ish times more than the amount of electricity that we use. And then second, it's just how we use it, right? We use a lot of gas and we use a lot at once, right? And this is one of the biggest challenges, is this kind of the slope of this line from 5 a.m. to 8 a.m. as the whole country wakes up. The gas comes on everywhere and goes up by about 100 gigawatts in the scale of 3 hours. The electricity grid, by comparison, turning on every single asset in the country, manages an 11 gigawatt jump. And then we struggle with that, right? We hear about constraints in electricity far more often than we hear about constraints in the gas grid. So both in terms of the total and in terms of the flexibility, the gas grid has no replacement really in the current system. But it will need to be replaced. This line will have to disappear if we're going to be serious about our carbon emissions. And so it's in theory possible for, I've seen projections that we could match the total with wind generation and other renewables and combinations of renewables, that the total under the curve, we could maybe get there, but it would be still very hard to match this capacity. So in other words, the shape of this line, the sort of load curve, is going to have to change quite a bit. And again, throwing back to Duncan's talks, there are some really great examples of how you sort of balance loads across a site and how to do that. In looking at the sort of combination of ingredients that we have to replace this blue line, it's a fairly short list. I really like the way that the Committee on Climate Change put this graph together. So it sort of shows, and each box gives roughly the portion of the solution that you could expect to get from that idea. So at the top, you sort of have 10, maybe 20% in savings from new build if we build everything with low carbon heat from now on. Most of our stock is already here, so that only gets you about 20% of the way there, and the rest is all in the existing stock. The orange box shows what you can get from energy efficiency improvements, just all the fabric first demand reduction stuff. It's obviously an important element, and we should maximize this as much as we can, but it's still not going to get us all the way there. Off-gas grid is a likely contender for heat pumps. We're talking about low carbon heat networks quite a bit, but there's this huge white box that's sort of unaddressed, which is likely going to be some combination of hydrogen, heat pumps. We don't quite know yet. It's a huge unknown in this whole puzzle. So very, very likely, what I think we will see is a sort of expansion of this idea of heat networks and low carbon heat networks in terms of what we think of as heat networks and what they can do. So we struggle to just build more and more and more of them because there's very high capital costs, installation costs, long-term planning constraints. But we're seeing more and more examples of sort of different versions of heat networks that are sort of easier to implement on a modular basis. So that's one of the examples I wanted to talk about here. So the Balanced Energy Network at LSBU is the first that we know of installation and actual commissioning of a 5th generation heat network in the UK. Now these are starting to gain quite a bit of traction, which is great to see. But the UK mostly has 3rd and some 4th generation heat networks. So just to describe the terminology, 1st generation was sort of steam, and then 2nd, hot water, sort of gradually reducing temperatures of hot water until we get to a low kind of ambient temperature water between 10 and 20 degrees in the 5th generation. So a simple way to think of it is as the generations go up, the distribution temperatures come down and the efficiency increases of the system. So we're seeing more and more interest in this type of 5th generation system. And LSBU is a really good example of one. So it uses boreholes, 2 boreholes, pulling water from the aquifer at 14 degrees and moving them between 2 buildings using this lightweight pipework. The pipework is just plastic. It's very lightly insulated, just basically to stop it from freezing. But it is more or less kept at ambient temperature until it gets to the buildings, where we ramp it up to a useful temperature using these high temperature heat pumps. So these heat pumps are interesting. They were specifically designed to address the retrofit question. How do you retrofit a heat pump into an existing boiler circuit without having to resize all your emitters and pipe work and do massive fabric upgrades and things like that without sacrificing the overall performance? So it's a really interesting look at just how you do that. And this is what we were able to do, is sort of to interface on the common header that the boiler circuit feeds. And we just replaced the first of the boilers with this in a cascade. And then all of the sort of peak loads are picked up by the gas. And this takes as much of the load as we can. The COP for the individual units is still around 3. The system efficiency comes down a bit for reasons we can discuss. The other component that we added was thermal storage. So these are 2 10,000 liter thermal storage tanks that we installed to sort of help shift the peak loads. And a very interesting thing about this that is still unique among heat pump, around heat network design, is integrating every single component of the network into a demand response addressable control system. So usually when we think about demand response, we link it to specific individual assets like a car battery or a standby generator or something like that. And what this did was integrated across every single electrical component in the network that we have and to the heating control system itself. So we're flexing not just the electrical loads associated with the heat pump, with the circulation pump, with the storage tanks, but also the actual sort of temperature of the building, the thermal mass of the building itself. So it really takes the idea of active demand response and integrates it into how the network works. It's interesting now, we're doing a paper as we speak, analyzing the performance of it up until now. And I think it gives a really interesting sort of warts and all view of how this kind of thing gets implemented. We basically, in the first year that it was on, had to do a lot of troubleshooting with other components in the system, right? The main priority was to not interrupt the temperature of the buildings. This is heating my office, and my office has thankfully stayed quite warm throughout. But it has revealed lots of other sort of hiccups in just how the building works that have sort of brought down the overall performance of the system and actually increased the costs. We modeled it as reducing costs by about 10%. Whereas what we've actually found is just kind of operating in baseline mode with all the other sort of hiccups and circulation pumps and things like that, we actually increase utility costs by about 10% because of that switch from gas to electricity. So right now, it is saving carbon just from this switch from gas to electricity that reduces carbon, but it has increased operational costs a bit. which it doesn't need to. We are currently kind of optimizing the performance to make better use of these addressable demand response assets and the storage and so on. So we will be reducing the costs over time, but I think it shows an interesting the interesting reality of getting these systems in is that you can do it one at a time. It does save carbon, but it does take a bit of effort to kind of make sure that we operate it as efficiently as possible. Because the kind of set it and forget it approach for gas boilers isn't quite as easy to do with heat pumps. The other project I wanted to talk about quickly is called Home Energy for Tomorrow, which is sort of a domestic version of what I was just discussing with our university campus buildings. So what this is a dual source heat pump. So the dual source nature refers to whether it's pulling heat from the ground or from the air. So it's both electricity. It's only sources electricity, not gas. And what it basically lets you do is pull heat from the ground source, which will give you a higher COP, until the ground heat sink sort of gets depleted. And then it switches over to air source until the ground recharges and then switches back to the ground. So it basically allows you to choose between the two heat sinks based on whatever gives you the best COP at a given moment. So it's a really interesting approach. And what it has shown is that you can basically get away with undersizing your ground source heat array by about half. So you have half the pipe depth if you're doing a borehole, half the sort of the ground source pipes. And then because you're only switching over to air source at peak times, your seasonal efficiency isn't really affected all that much. So it's quite a remarkable way to add flexibility to a system, right? By having the ability to toggle between these two and really reduce the costs of a ground source while maintaining the performance of a ground source. So to sum up those projects, right now, I think it's important to highlight a few of these features, that you can retrofit a high temperature heat pump into an existing heating circuit. You can deliver a good COP and improve that over time. You can create a dual source heat pump that lets you reduce the size of the ground heat exchange that you need. And you can use demand response control systems to aggregate loads across your network and shift peaks. And then to reduce costs, which is what we're exploring right now, is flexing tariffs and using DSR revenue and other kind of, well, RHI while it's still there, other options to sort of reduce the cost. So with all of these, why is gas still our default option for heat? I think this is an important idea to discuss. A very large part of the market is still just waiting for hydrogen. We have a lot of interest and investment from the government, from the industry, looking into how we can convert the gas grid to hydrogen. And there are a lot of big questions around this. The plan would be, and it's a fair plan, to have hydrogen-ready boilers sort of phased in over the next decade. So these don't exist right now, right? Every boiler in the home, you would only be able to fire gas. If you were to replace the gas grid with the hydrogen, you would need to replace every single appliance. So the plan would be to sort of phase that in with a bunch of hydrogen-ready gas boilers that still use gas but are ready for that switch when it comes. And that's a fair plan, but I don't think there's any realistic pathway that puts that any sooner than a decade from now. The Leeds City Gate project and other analyses, we're all kind of maybe looking at a few examples at the end of this decade, but mostly it's a solution coming along in the 2030s, which makes a really big problem. What do we do for the next decade while we wait to know the future of the gas grid? And I think that's a really important question for the building services industry, for our sector to sort of grapple with. Most decisions are really waiting on that gas grid infrastructure question, and we are avoiding low carbon heating system upgrades and focusing on fabric first, which is sensible. We should focus on fabric first, but we should focus on fabric first and the heating component, because there are efficiency gains in the whole house approach that we really can't be neglecting these questions about where our heat is ultimately going to come from. And we continue to install about 1.2 million new boilers each year, maybe more, depending on what kind of boilers you count, including in that category. It's at least 1.2 million per year. So if we continue this trend for 10 years while we wait for the hydrogen situation to come along, it will very likely dig us into a hole that would be difficult to come back from. It's interesting in a way. I like this number 1.2 million because it shows that we are installing 1.2 million heating systems per year. We're just installing the wrong kind, but at least the sort of supply chain is there. This is how many low carbon heating systems we need to be installing. So what we need is to, as building services engineers, slowly nudge this, slowly but not too slowly, one boiler at a time, nudge this into low carbon installations per year while we're waiting for these questions about hydrogen. I would put it sort of that way, that we need to kind of challenge the gas status quo wherever possible. So I would kind of sum it up with those 2 points, that we need to seriously question every gas boiler installation that goes in, that it not be the default, but if we do need to, at least we've considered and exhausted the other options. And the other options should include and encourage technology neutral transitions wherever possible. So those examples from LSBU are great demonstrations because they are technology neutral. They do not preclude any other options. They're hybrid solutions. They work in parallel with existing systems. It's taking out one boiler at a time so that you're not making distressed purchases, replacing more boilers with other boilers at end of life, and you sort of gradually improve how your system operates after you get started. It provides sort of baseline performance for how you can sort of improve that performance with time, right? Those buildings still use gas. They just use less gas than before, and it's a bit of movement in the right direction. And the data helps inform future systems. We will eventually need to know how much hydrogen we need. Putting in systems like this help us sort of determine those questions with actual demonstrators, not just models. And as we say, encouraging this kind of hybrid idea, the idea of having multi-vector systems that can toggle between different sources does not lock us into a particular technology pathway, and it's stuff that we can get on with in the next 10 years while we wait for these big infrastructure questions. So I would kind of leave this up here for questions before I hand the screen back. I do think we need to encourage in our discipline as building services engineers more of a conversation about how exactly in the next 10 years we can drive this transition from gas to low carbon heating. One question is simply around specifying gas boilers in new builds. How can we move away from that? How do we challenge the sort of status quo, those 1.2 million going into existing builds? And how do we grapple with costs? I mean, it's enormously stacked against us. Cost is obviously the dominating factor, both on a capital cost and an operational cost basis. The case for operational costs is getting better. As I say, we can use that flexibility to reduce the operating cost, but it's still an uphill battle, but it's one we have to grapple with because we can't just sit around for 10 years waiting for a silver bullet with this. So we need to come up with ways to engage clients that can start to overcome this. So I will leave it there. I've seen quite a few questions that hopefully we can come back to. I'm going to end my presentation here and switch it over to Letitia's screen. So I will introduce Letitia quickly as she's getting set up. Hopefully she can project her screen on. Dr. Letitia Mottet is a postdoc research associate working at Imperial College London and the University of Cambridge since 2016. Dr. Mottet was in charge of the computational fluid dynamics aspect of the low carbon climate responsive heating and cooling of cities project and investigated the outdoor and indoor motions of air to quantify the efficiencies of the adaptive solutions proposed. So over to you, Letitia.
Yeah, I'm trying to set up my screen. Wait a minute, I need to swap display. Here you go, right? Okay, great. So thank you very much. So good morning, everybody, and thank you very much all for joining this webinar. So today I'm going to talk about a the local research project, which is a research project. So basically my talk will be less engineering oriented than the previous talk. So the LOCOOL project, so LOCOOL is standing for low carbon climate responsive heating and cooling in cities. And this project is now finished and was led by Professor Alan Short from the University of Cambridge. So in the current world context in which we are restricted to travel, I would like today to make you travel a bit, and I would like to go in a beautiful country, which is, now I think you can see which country I'm talking about with the little video you're watching right now. So we are traveling in China. So China is a beautiful country, but unfortunately, China is also very well known for its pollution issue. So basically, between 1980 and 2007, the energy consumption in China has increased by about 340%. And sadly, the CO2 emission associated with the energy consumption has also increased by about 352%. So basically, the building sector is responsible of 40% of the national energy consumption in China, and the HVAC is responsible of about 19 to 21% of the national energy consumption, which is a lot. And so the building sector itself releases per year around 2.2 billion tons of CO2 in the atmosphere. So basically, this is something we need to tackle, or China need to tackle. Well, it's not only a problem or an issue in China. So our project focus on China, but this can be applied everywhere, actually, around the world. So more particularly in China, I will talk about it later, but we can divide China into climate zone. And in the local research project, we are interested by the hot summer and cold winter zone. And in this zone in China, there is about 30% of the Chinese population living there, which is about 550 million citizens. And there is around 9 billion meters square of floor space, and 66% of it are residential buildings, which can be retrofit to decrease the energy consumption. So how we propose to reduce the CO2 emission in China? First, we want to reduce the heat ventilation and air conditioning consumption in China. And how we want to do that? How we want to achieve a low carbon future during the hot summer in China? And we want to answer this question by encouraging the use of natural ventilation and by developing a catalog of adaptive schemes using natural ventilation for existing buildings. So the local project is a partnership between 5 different universities, 3 in UK, which are the University of Cambridge, Loughborough University, and University of Reading, and 2 Chinese universities, Zhejiang University in Hangzhou near Shanghai, and Chongqing University in Chongqing. And this project was led, as I said before, by Professor Alan Short, which is, I think, today in the attendee during this webinar. So let's start with the methodology we followed during this research project. So first, I mentioned it briefly before, but China can be divided into climate zone. And we are particularly interested by a zone which is called hot summer and cold winter. So how you can imagine in this zone, the summer are very, very hot and the winter are very, very cold. And into this region, we focused on 2 different cities, which are Chongqing and Hangzhou. And in these 2 cities, our Chinese colleagues sampled the buildings in order to classify which type of building, a typical building there is. And so we ended up having an area in Hangzhou, including 95 buildings, and an area in Chongqing, including 542 buildings. And based on this area, well, not only, but based on this area, our Chinese colleague defined different type of very typical Chinese building and very typical residential building. And they ended up mainly with 2 main types, which are tower building and slab buildings. So basically, we focused then in this project on 3 test case buildings. So 1 tower building in Hangzhou and 2 slab buildings, 1 in Hangzhou and 1 in Chongqing. So what we actually did for this project is to link 3 different fields, which are the architecture led by Professor Alan Short, building energy simulation led by Dr. Ji-Hoon Tsang, and computational fluid dynamics, which I was in charge of that. So basically for the building energy simulation, Dr. Tsang used Energy Plus, which is building energy simulation program used to model energy consumption for heating, cooling, ventilation, lighting, and so on. While myself, I was using for the CFD software, the software Fluidity, which is an open source finite element software developed at Imperial College London. And its main advantage is the use of unstructured and adaptive mesh. I'm not going into detail of that, but if you have questions, ask. So I will start to focus on the tower building I was mentioning before. So it's basically a 23 stories building, 74-meter height. You can see a 3D view of it here. So basically this building, we call it butterfly building. So it's not a very common type of tower in UK, for example, but it's a very, very common shape in China, this butterfly tower. So it's really a good test case, because what we will do, what you will see after, what we did on this tower can be really applied on a lot of different buildings in the Chinese climate zone. So what we did first is we looked at the current thermal condition of the buildings. So Dr. Song did this exercise, and here we will focus on the plot on the right. Hopefully you can see the different colors for the lines. And let's start to focus on the red line, which is the one at the top of the plot. You can see this red line is actually the indoor temperature in flat 6. This is just for an example, but in flat 6. And you can see the indoor temperature during 1 month, which is the hottest month in Hangzhou, is between basically, let's say, 35 and 39 degrees, which is really high, which is definitely not comfortable at all for people. Okay, that's it for the indoor temperature. Now let's have a look at the outdoor temperature, which is the green line. You can see at the bottom of the plot some spike of the green line. So basically the outdoor temperature is between 25 and 30 degrees, which is something like between 5 and 10 degrees lower than the indoor temperature. So we were thinking like, well, why not using the outdoor temperature just to reduce the indoor temperature and make people comfortable? So Dr. Song did the exercise to just increase the ventilation rate into this flat, just to see if we were able actually to reduce the indoor temperature. And these are the other lines you can see on the plot. So basically the blue, red, and violet and black lines. And yeah, if we increase the ventilation rate in this tower, we can definitely decrease the indoor temperature and make the people feel comfortable and use less air conditioning during hot summer. So we were thinking like, well, why people are not just opening their windows to reduce the indoor temperature? I mean, what's happening here? What's the problem with this building, right? So we did some CFD simulation, some computational fluid dynamics simulation, and based on that, we had access to the pressure field along the facades of the building. And based on that, we are able to compute the maximum ventilation rate we can achieve in a specific flat based on the pressure field along the facade. And computing that, actually, we figure out that the maximum flow rate we can achieve by just opening the windows are so low that we will never be able to bring enough fresh outdoor air into the indoor space to be able to reduce actually the indoor temperature. So that's just a fact. If they open their windows, they won't achieve thermal comfort at all. So just to mention, when we are doing our CFD simulation, we also have access to the wind pattern around the building. So we are able to identify where we have high wind speed zone, low wind speed zone, where we have air circulation and all this kind of very interesting and useful information when we want to implement some natural ventilation scheme into a building. So based on all this information, Professor Alan Chant came with this a new innovative and amazing design, able to improve the natural ventilation into this tower. So basically, this design is based on wind catchers and chimney. So how it works? Basically, the wind catchers are catching the outdoor wind, and this air is going into the flat, and then the outdoor hot air is evacuated by the exhaust chimney. So one chimney is linked to 7 flats. So this is the design Professor Chant proposed, and then we were like, okay, well, now we need to see if it actually works. So what we did is we added this design into our CFD simulation, and we rerun our simulation to see if it was behaving as expected. So here you have an animation of the airflow into two flats. Actually, you can see the wind catcher on the right part of the animation. The chimney are not here on this animation, otherwise you won't have been able to see anything because they should be on the left part of it. But you can see, I guess, the pipe which are going towards the chimneys. So basically, we can see that the air is well mixed and going into every room. We are not having uncomfortable draft because, for example, the airspeed in the living room is about 0.1 meter per second, which is quite low. And with this scheme, we can increase the maximum ventilation flow rate by about 32 to 63% into this flat, which is quite a lot. And the average reduction of temperature we can achieve into the flats are about 4 degrees with a maximum of 7 degrees, depending which level and the orientation of the flat. So that's for the tower building. And so basically we did and followed exactly the same methodology for the slab buildings. So as I mentioned before, for this type of buildings, we had 2 test cases, so one in Hangzhou and one in Chongqing. So I should have mentioned it here maybe, but on the left part where the building having 6 stories is in Hangzhou, and the one having 9 stories is in Chongqing. And we basically did exactly the same and followed exactly the same methodology. We look at the current situation of the building and exactly the same conclusion. So basically, the outdoor temperature is always lower than the indoor temperature. So same question, why they are not just opening their windows to reduce the indoor temperature? And the answer is exactly the same, because under the current situation, if they open their windows, the maximum flow rate they can achieve is so low that they can't reach thermal comfort. So based on that, Professor Chant came once again with some amazing new designs able to improve the natural ventilation. So the design are different into these 2 buildings because we wanted to compare the efficiency of 2 different designs. So the designs proposed in Hangzhou on the left is based on 2 wind catchers. And the wind catchers are basically playing the role of inlet, outlet, or inlet and outlet at the same time. While the scheme, the design proposed for Chongqing is based on wind catchers on one side of the building and chimneys on the other side of the buildings. So here, contrary to the tower building, one chimney is linked to one flat. So yeah. And then once again, we did some CFD to check out if these designs were performing well and were doing what we expected. And so the design based on 2 wind catchers was able to increase the ventilation rate up to 3 times compared to just opening the windows. And the design based on one wind catcher on one side of the building and chimneys on the other side, were able to increase the ventilation rate by about 5 to 9 times, which is quite a lot actually. And once again, we wanted to check out how much we are able to reduce the indoor temperature. Once again, we want to reduce the indoor temperature to avoid people using air conditioning, and because this vicious cycle of air conditioning, CO2 emission, energy consumption, CO2 emission, and so on. So the temperature reduction we can achieve in Hangzhou using the 2 wind catcher design is about 5 degrees, while the temperature reduction for the design based on wind catcher and chimney is about 3 degrees. So short conclusion, so this project now, the local project is now finished, but we show that it's actually possible to link architecture and building energy simulation as well as computational fluid dynamics to be able to propose designs that are physically checked by building energy simulation and computational fluid dynamics. And so we ended up having a catalog of solutions for a common residential building type in China. And just as a short conclusion, Monica Cook with her company Cinetecture did a short movie of 10 minutes summarizing this project and the main output of this project. And we actually won last October the Global Sustainability Film Awards in the AI and digital innovation category. And I really encourage you to look at this movie. You can find it easily either on YouTube or on the University of Cambridge website. If you just look at search for low carbon or China Furnace City, or even if you are looking for Professor Alan Short web pages, you will find it very easily. And I really recommend you to go and watch that short movie. Thank you very much for your attention, everybody.
Thank you very much, Letitia. That was great, really interesting. So we've run just past the 12 o'clock mark now, but we're going to answer just a few questions if anyone is able to hang on. And either way, all the questions will be kind of received by email. So please do continue to submit them. We'll take just a couple minutes to answer a few questions because I think there's some really interesting points raised. So first is for Duncan. Let me find the one here about CHP. So the question was, Duncan, could you comment on how to optimize the use of CHP in the rundown of fossil fuel use?
Hi, Aaron, thanks for that. I think at the moment where CHP, this is presumably with reference to natural gas-fired CHP. So in terms of that, it depends very much on the particular situation and how you can integrate it with other newer energy systems. Obviously, there are CHP units that are still in operation, may still have a reasonable amount of life left in them. Ideally, they would be run at times when there's a higher grid carbon factor, because that allows them to effectively stack up better against imported grid electricity. I think a longer term argument against obviously gas-fired CHP is that as the grid is decarbonised, the benefits of CHP from a carbon perspective diminish until they actually become negative. So whilst the grid is as it is, ideally they would be mainly run in terms of higher carbon intensity in the grid. So that is times when you've got low wind power, low solar coming into the grid, and you're relying more, for instance, on coal and gas. So that would be the ideal use with respect to carbon. With respect to the actual cost benefits, then that very much depends on the tariffs that are available. If there's a different range of tariffs that are available in terms of preventing the import of electricity or potentially even export electricity, and whether there's any opportunities to use them to provide a degree of DSR, i.e. if they were coupled with thermal storage, could they export electricity or reduce demand in periods of high demand on the grid? So from that perspective, they would they would benefit the wider kind of low carbon infrastructure on the grid, as well as providing a revenue stream.
Okay.
Is that okay?
Yeah, thank you. Great. I'll answer a very quick one that was for me, was if people could come and tour and view the installations that we have at LSBU. And the answer is yes, of course, we would love to. The whole campus is shut down at the moment, as much of us are in the same boat. But as soon as life goes back to normal, we would love to have you around and show you the demonstrators that we have there. So yes, please do email me if you want to line up a visit. Letitia, a good question for you about air quality. So how do you deal with issues of poor outdoor air quality and bringing more polluted air into the buildings?
Yeah, that's actually a really, really good question. I have this question all the time. I should definitely had one slides when I present this project about that. So we actually did some air quality simulations. So I'm not showing it, but in my CFD simulation, I'm mimicking the pollution by traffic, and we are able to see where the pollution is trapped and around our test case building, and it's how we decide where we put wind catchers. So we decide to put wind catchers where we have less pollution trapped around our building. But of course, in addition of that, what we need to do is to add some dampers at the wind catchers inlet to close them when we have a very high outdoor pollution episode, to be honest. Yeah, I think that's my answer. But we look at this actually.
Okay, great. Thank you. Yeah, so a lot of people were asking about the recordings, and yes, these will be made available, and we will be receiving all these questions by email, so we'll follow up with as many as we can. We're going to leave it there for today. Thank you, everyone, for joining us, and hopefully we'll have some good follow-up conversations. So thank you all, and hope everyone can stay safe and healthy. Cheers.